All right, so just a couple housekeeping stuff before we jump into things. I'm going to put up today another Learn Smart that I want you to try. I want you to read and go through prior to Wednesday's class. There'll also be an online quiz today. It's due before Monday's class, and then we have those current homeworks up there I want you guys to start working on as well. Any questions from you before we kind of jump into things here? We got a couple people on Zoom and one person here, so this is it's gonna be weird. I guess I'm just talking to you today. So, so up to this point, what we've been talking about is having a variable that has a population mean and a population variance that we know, right? We're going to now kind of transition to, we've taken these samples, we've tried to reduce as much bias as we can, and we're going to calculate a sample mean from it. Now our desire is this sample mean is really close to the population mean, because we can't see the population mean, and we're using like the sample mean as the best, best measure we've got. So we're going to talk about things that we can do to make sure that the sample mean is really close to what that population mean is. So one thing that we need to know is, if I were to take, say, 1,000 different samples of the same size and then plot those as a distribution or take a histogram, those sample means, those 1,000 sample means would have their own distribution, right? So if I take samples of different sample sizes, that distribution will change, right? So I want to think about, how do I think about this? So if I took a sample of size 1, I could see the sample mean be, that's, if I'm looking at human height, I could see 7'2". I could have randomly sampled someone who was 7 feet tall, 2 inches, right? But if I take a sample of size 100, there's no way I'm going to see a sample mean height of those 100 people be 7'2". So the idea is that I can take samples of size n, but as I take different sample sizes, that impacts the distribution of those sample means I'd be looking at. Right? So it ends up being true, and for now, just kind of take me at my word, I'll walk through a data replication to kind of show this to you, is that if I looked at those sample means, so I took 1,000 different samples, let's say they're all sample size 20, the mean of those sample means, 1,000 sample means, would be whatever the population mean was from the data that I was sampling from. The variance of those sample means would be whatever the variance was of the original variable I was sampling from divided by my sample size. Okay? So this is the idea that if I only take samples of size 1, I could see sample means of 7'2", 4'11" for human height. If I take samples of size 100, it's very unlikely I even see a sample mean of 6'6" for 100 people, right? So the idea there is my range is getting smaller for higher samples, or that if my sample size gets larger, right, my denominator gets larger here, that would reduce the entire fraction. So for higher sample sizes, I'm actually reducing the variance for that distribution of my sample means, okay? Now the mean of my sample means is unaffected by the sample size. It's always just gonna be whatever that population mean is, okay? And the intuition behind this I can give you is, let's say I had a population, I calculated its mean, like I have the actual data. I'd get the population mean. If I start to take samples, and I take enough samples that eventually I have every single person from my population in one of my samples. Well, now when I'm finding the mean of those sample means, it's really just like I'm finding the mean of every single person, right? That's kind of the intuition behind this. Or a good way to think about it, I should say. So we already kind of hopefully know what these are. This represents my population variance, and is of course my sample size. We mentioned in that last class, and we've dealt with that before, okay? So if this is the equation for my sample variance, I've already mentioned the sample size will impact it, right? As my sample size goes up, then my variance of my sample means goes down. But also if the original data has a higher variance, then my sample means variance will also be higher, right? So these are kind of the two components. Now, one thing that I want to point out before we get too far into things, because we'll see it written both ways. The standard deviation of my sample means, well, if this is the variance, we could just take the square root, right? So my standard deviation is just the square root of the variance. But I can write this in two different ways, right? When I take the square root of sigma squared, these kind of cancel, I'm just left with sigma. And then I would still have in the denominator the square root of n. So these are really the same thing, just written a little bit differently mathematically, okay? And we'll see them, depending if we're given the variance or we're given the standard deviation, sometimes one of these is easier than the other to use. Right? And then this is a rule of thumb. This just means our sample sizes can't be too large. I'll never give examples where this doesn't hold, so we don't have to worry about this for right now. So if I had an example, right? Let's say I had every single birth in Indiana. I can observe the population mean for Indiana births in that year because I have every single birth that ever occurred. I calculate that population mean and I calculate the population variance. If I then from this sample randomly selected 36 births, right, I could calculate the sample mean of those 36 births. I could then take another sample of 36, calculate the mean of those 36 births, sample another 36, continue to do this so that I have like an infinite number or a very large number of sample means. Well, now that I have kind of all these sample means, like let's say I was storing them in Excel, well, I can find the mean of my sample means by taking the average function, and I could find the standard deviation of those sample means, right, by using the standard deviation function in Excel. So if I were to do that, what would these be? Well, we said in the previous slide, the mean of my sample means will always just be whatever the original population mean was of the data I sampled from. The variance will be whatever the original variance was of the data I sampled from divided by my sample size. So when we look at our example here, the mean of my sample means will just be the original population mean. So we know it has to be 3,287, so we know it's either A or C. From there, well, we know the standard deviation, right, would just be, I just grabbed this marker, it's brand new. It's not writing very well. Give me one second. I got another one here. Just grab this because the one I had last class wasn't working very well. Let's try this. There we go. Should just be the square root of my population variance over my sample size. Okay? So if I was thinking about the example that I just had, this was the square root of 360,000, and I sampled 36 births, right? If I enter this in my calculator, I should get 100. Okay? Now the other format we had was take the standard deviation, divide by the square root of n. So I could have first taken the square root of 360,000, found out that this was, what, 600? Plug in that 600, divide by the square root of 36. That would still give me 100. So either formula would work there. It's just a matter of which one you kind of find easier. So, get this out of the way. There we go. Right. If we plug it in that format, we get the answer of 100. I kind of showed you we could have done it the other way as well. Still would have found that standard deviation of my sample means is 100. Okay. Any questions on that one? Or keep moving? You good? All right, so when I say are there any questions, I guess if you're going to say yes, I'm waiting for people in the chat. So let's think about if instead of 36, we took samples of size 100, right? So if I take a sample of size 36, I found that the standard deviation was 100. So if my sample size increases, what should happen to that standard deviation? Well, if we go back to this equation, if the sample size goes up, I'm dividing by a larger number, the standard deviation of my sample mean should go down, right? So if with a sample size of 36, I found the standard deviation was 100. When I take samples of size 100, I know that the new standard deviation has to be less than 100, right? So when I think about here, it would have to be one of the standard deviation answers that had 60, because 600 would be greater. Right? Now, no matter what sample size we take, the mean of my sample means will always be the population mean. So we know the mean of my sample means will always be this population mean of 3,287. And I know that standard deviation has to be smaller, so I could have known it has to be 60. Now I can actually go ahead and use the exact same formula I did here. The only thing that changes, instead of 36, I'd be plugging in 100. Right? But I just want to kind of use that to point out, if we had done prior work, we know that with a higher sample, that standard deviation has to be lower than it was before. Right? This is kind of another way of looking at that exact same thing. If I start out with my original data, I take a sample of size 5, a sample of size 50. Notice that when I take higher samples, the distribution of my sample means that variance should be going down, which with a lower variance means more of the values I'm seeing are right around that mean, right? And so I get this more peaked distribution. We said when the variance is low, I get a real peak distribution. When the variance is high, I get a flatter distribution, okay? So as I start to take samples of higher sizes, I get a more peak distribution, which ultimately, and I'll draw something up here in a second that hammers this idea home, that if I take more observations, I'm getting a better estimate of the population mean, right? I have more of the population in my sample, right? And the reason why taking a higher sample size will ensure that we're more likely to get a value that's close to the population mean is because if I think about my sample means, let's say I took samples of size 10, right? I would have, and for right now, let's say assume we're sampling from a variable that's normally distributed, so my sample means will also be normally distributed. If the sample was size 10 here, and then I have one where I have a sample of size 50, well, the mean of both those sample mean distributions will be whatever the original population mean was. But notice when I take a higher sample size, because I know that higher sample size would reduce the entire fraction or reduce the variance, smaller variance means more peaked distribution. When I take higher sample sizes, the values really close to the mean have much higher likelihoods of occurring, right? So by taking high sample sizes, I've increased the probability I see a sample mean really close to the population mean, and then I've decreased the probability that I see these values that are really far from the population mean. So this is why it's important that we know that this variance is linked to that sample size, because by taking higher sample sizes, I'm getting this more peak distribution and narrowing down, or sorry, decreasing the likelihood I see values that are further from the mean. Okay. All right. And I have kind of another visual of that here, where you can see if I take a sample of size 1, the number of times I see values, this was like a little simulation, the number of times that if I randomly sampled, I saw values near this mean of 50 when the sample size was 1 was a very small number of times. Whereas when I take a sample of size 50, the sample means that I see kind of centered around that population mean of 50, I saw that happen way more often, okay? All right, so, and this was just, like I said, this was like some simulation data from just randomly generating kind of numbers from 0 to 100, and then taking samples of different sizes, finding the sample mean, the number of times I see the sample means of these different values. So, didn't explicitly mention this, but we have the equation for how I find the mean of my sample means and the variance of my sample means. What ends up being true is if my original variable I'm sampling from is normally distributed, my sample means would be normally distributed as well. But what happens if that variable that I'm sampling from isn't normally distributed? So let's say X is uniformly distributed. Well, will the sample means also be uniformly distributed? And will the mean of my sample means still be the population mean? Will the variance of my sample means still be the original variance over the sample size? What ends up being true is, yes, all those things still hold. It'll still be normally distributed. The mean will be equal to, the mean of my sample means is the original population mean. The variance of my sample means is still the variance of the original data over the sample size. As long as we have this central limit theorem being met, which is if we take a sample of size 30 or more, so I have greater than 30 here, kind of think about greater than or equal to would work. As long as that sample size is 30 or more, then I know that my sample means will be approximately normally distributed. The higher my sample size gets, the closer and closer of an approximation that I'll get. Okay? So that, once again, it's better to take higher samples because I'm getting closer and closer to a normal distribution for my sample means. Right? So kind of nice little visual of this is like a replication with 4 very different distributions, right? These are 4 different variables. They start out, the original data, very different distributions. We've got one uniform. This one kind of looks like an exponential, but very different, okay? If I take samples of size 2, calculate the sample means, and then draw the distributions for each one of these variables, like sampling from each one of these, I don't really have any normal distributions here. At 6, this one and this one look normal, but these are still pretty skewed. Once I get to 30, all of these are such a close approximation of the normal distribution that to our naked eye, right, I can't really see much of a skew in any of these here. Excuse me, okay? So we can use this, right? And we could walk through the proofs, mathematical proofs of why once we get a sample size over 30 that's a close enough approximation to a normal. Or I can just do a data replication to try to hopefully convince you that this is true. And this is actual data that I did this with. I'm not just like, it's not I put the numbers on the table. So I had every Indiana birth in 2004, right? So I've got the population data for Indiana births. There's 4 variables. So whether the birth weight, the length of the pregnancy or the gestation period, a health measure of the child, which is the APGAR score, and then whether or not the mother smoked. Right? So the maternal smoking information is just 1 if the mother smoked while pregnant, 0 if she didn't. So if I had that data in Excel, I could very easily find the mean and the standard deviation for each one of these variables. So that's what I did. Right? Here's the mean birth weight. Here's the standard deviation. Here's the mean length of a pregnancy. Here's the standard deviation. Right? This is kind of sad, but the mean, right, smoking use is 0.18, which means 18% of mothers in Indiana smoked at some point during their pregnancy, or 82% didn't. But we've got our mean and we've got our standard deviations here, okay? I then can look at the distribution for each one of these variables. So the birth weight variable starts out nice and normally distributed, right? We can kind of see there's kind of premature births that are very low. We've got some really fat babies up here. But it's a really nice normal distribution. The length of the pregnancy or gestation, yeah, can maybe starts to look kind of normal, but has this like longer left tail. So we have some left skew. This is the idea that we got some babies being born at 6, 7 months, not really any babies being born at like 11 months. Okay? The health score, not a lot of variation in it. We can kind of see, I guess, a little bit of a left skew here. And then I didn't draw it, but what would the maternal smoking variable look like? Well, we only have 2 responses. 1 if they did, 0 if they didn't. So it really would look like who didn't smoke, 0.82. And then who did smoke, that was 0.18. Right? So we don't even start out with a continuous variable here that we're sampling from. But that's okay. Because we're not concerned at this point, where I'm trying to get to, is that we're not as concerned about whether or not this original variable is continuous, but the sample means would be continuous, right? Because if I take samples, I can see 0.18, 0.193, I could see these different values for the sample mean, okay? So the sample means will be continuous. So that's all we're kind of concerned with when dealing with that normal distribution. So what I did then, so I had the original data, I looked at the distributions, I found the mean and the variance. I then took samples of size 100 for each one of these variables. I looked at that sample of 100 and I calculated the sample mean birth weight, the sample mean gestation, the sample mean APGAR score, and sample mean maternal smoking for that sample. I then did that 1,000 times. So I took 1,000 different samples of size 100. All right? Well, now that I have these 1,000 different sample means, I can find the mean of those sample means for each variable, and I can find the standard deviation of those sample means. Right? Like once I have a column of these sample means, equals average, select the column in Excel, equals STV.S, take the standard deviation. So if I do that, what I told you is true is that the mean of those 1,000 sample means should be close to whatever these original population means were. And the standard deviation should be equal to the original standard deviation divided by the sample size. Sorry, divided by the square root of the sample size. That was from that equation we had earlier. Well, if my sample size was 100, the square root of 100 here was just 10. I chose that sample size 100 because now that really just means we're moving the decimal point one place. So if I look at the original mean and standard deviation of each variable, I then have my 1,000 different sample means of sample size 100. I calculated the mean for each one of these variables from these 1,000 sample means, and I found the standard deviation of these 1,000 sample means. Notice they're a little bit off, right? I'm rounding the integer here, so they're actually not even one off. It was like, you know, this is 3,287.3, and this is 3,287.9, but they round to a kind of different integer. But it's a very close approximation, right? This is, you know, the mean of these sample means is pretty much equal to the population mean. Very close here, very close here. I mean, these are identical, right? Now the standard deviations should be divided by the square root of our sample size, or the square root of 100, or 10. So 600, sure enough, we get 60. 2.6, sure enough, we get 0.27. And really here, the reason why these look a little bit different is I'm kind of rounding to the second decimal, right? 0.38 divided by 10 should be 0.038, so it gets rounded to 0.04. So we're getting exactly what we said was true with this data replication. Now, if I look at these numbers and they are a little off, the reason would be is that the theory is based off of an infinite number of sample means. I'm only taking 1,000 here. So I'm going to get very close approximations at 1,000, but theoretically, in order for it to hold, if I had a data replication that would exactly nail the values, I'd have to have an infinite number, or a number a little bit closer to infinite, which it's not really a number. So it's kind of hard to think about what that would look like, but you know, 10,000 instead of 1,000 or something, okay? So hopefully this kind of convinces you of what I'm saying is true. No matter what the variable started out as, the mean of our sample means was equal to the population mean, and the standard deviation followed the formula that we had for it. Now, what I also said is the distribution of our sample means should all now be normal. So I look at the distributions of my sample means on birth weight. I mean, this is picture perfect normal distribution. Length of the pregnancy, picture perfect normal. APGAR score, we get a normal distribution, maybe a little bit of skew still, but we said it's approximate to a normal. And then this one is a little choppy just because of how I created the bins here. If I would have went from like 0.12 to 0.13 and then 0.13 to 0.14, it created more bins. It looks a little bit more nice, but pretty close approximation to a normal distribution, right? Now, what also happens is when I'm thinking about taking higher samples, that reduce the range of values I could see. So if I think about just the original data on birth weight, I was seeing values from what, 500 up to 5,000. Well, when I look at the sample means, the variance of the original data gets reduced by dividing by the sample size. So if the variance is smaller, it's going to be like seeing a smaller range of values. So sure enough, when I look at the sample mean birth weights, I only see sample means from like a 3,000 to 3,500. And that's because these extremely high and extremely low birth weights get averaged out when I'm looking at a sample of 100 births. Right? Same kind of idea for each one of these other variables. I get kind of a more narrow range of values that I could see for that sample mean. Okay? All right, we're getting time here. Are we good? Any questions up to this point? Check the chat here. You good with that? Okay. So now that I know this, right, what I can do is say, all right, does that central limit theorem apply? Do I have a sample that's over 100? If it does, I can start to find things like, well, what's the probability if I took one sample that the sample mean for birth weight was over 3,000, right? Well, I'm looking for, like, I have a cutoff. I want the probability it's greater than that, right, or to the right. But I know that sample mean variable is normally distributed. So if I know that it's normally distributed, and I now know what its mean is, I know what its variance is, I can convert that into a z-score or a standard normal distribution, right? And then follow the same steps I was doing before. Once I have that z-score, and I'll come back to this in a second, well, what region do I want? Do I want the area to the left, the area to the right? Look up the relevant probabilities in my z or my standard normal table, and then transform those. You know, that was the idea. If I wanted the probability it's greater than a certain value, I could look up the probability it's less than that from the table and then subtract it from 1. So the only thing that really changes in our process is this z-score equation, okay? So I'm going to take a step back. Why does that z-score look a little bit different? So before, when we just had the original population data, we could think about different cutoffs for x. We then subtracted the mean of x and divided by the standard deviation for x, okay? The z-score for our sample means, well, we're no longer looking at the variable x. We're now looking at values for our sample mean. We'll then subtract the mean of our sample mean and divide by the standard deviation for our sample mean. But another way of thinking about this is, what's the mean of my sample means? It's always just going to be my population mean. What's the standard deviation of my sample means? Well, we could write this as the square root of the population variance over my sample size. Or I think how I have it in the slides is the other way, right? Mathematically, that's the same as the standard deviation divided by the square root of my sample size. So when I work through an example with some actual values, you can always use this formula and just plug your values in, or you can first calculate what that standard deviation of your sample means is and just plug that guy into the denominator. So I could just use this equation, whatever this value is, and plug that into the denominator. Okay? So it's really no different. For the z-score, we always take the statistic we're interested in, subtract the mean, right, of the statistic that we're interested in, and divide by the standard deviation of the statistic we're interested in. It's just that now that standard deviation for the statistic we're interested in has an equation that we would have to use to find it. All right, so let's work through one with actual values. So let's say, and my slides are a little goofy here. I cut this off so it looks a little weird. So I'm going to hit enter so we can actually see this. So this was kind of running into the slide or the line above it. So let's say I have this variable x. It's normally distributed. I know its mean. I know its variance. If I take a sample of size 100, what's the probability that from that one sample of size 100, I see a sample mean between 10 and 15? Okay. So I'm going to draw out what we're looking for here. We start out with, we're looking at values for this sample mean. We're told that the original variable x that we sampled from had a mean of 5, so we know that the mean of our sample means is equal to that population mean of 5. Okay? We're then asked what's the probability that we see the sample mean be in between 10 and 15. Okay? Well, right away, what do I know this probability has to be less than? The area to the right of the mean should be 0.5, so this has to be less than that. Right? So, what's the next step? I need to convert these values into z-scores. Right? Once I have these z-scores, I can look this z-score up, find the area to the left of it. I can look this z-score up, find the area to the left of it. If I subtract the smaller one from the larger one, I'll be left with just what's in between. But when I'm calculating these z-scores, what am I going to do? So let me see if what shows up here in the video. So I've got one way I could do this is first find that standard deviation of my sample means. I know that that's going to be equal to the square root of my variance over my sample size. The variance that we were told was 2,500. My sample size was 100. So if I actually do this, I get what? I think I actually get 5. I've added that in my calculator. So then to find this z-score, say for 10, I'll take that cutoff value I'm interested in of 10. I'll subtract the mean of my distribution, which is 5, and I'll divide by the standard deviation of my sample means, which is also 5, and I get that that z-score here is just 1. Okay. Now, the second one's kind of easy because if my standard deviation is 5, 15 is 10 away from 5, which would be 2 standard deviations. This, So I know that if it's 2 standard deviations away from the mean, well, that's the interpretation of my z-score. I should just have a z-score of 2. Sure enough, if I plug in 15 into that equation, I'll get that z-score of 2. Okay. Now, I could have done this a different way. All right? So I'm going to erase this real quick to show you that I could have done that. So just a little more. I could have just used the formula here and plugged everything in. So the cutoff I was interested in was, say, 10. The mean was 5. Square root of 2,500 divided by, wait, what was my sample size again? 100, right? And this will still give me that z-score of 1. Now, I personally think I like doing it the other way, where I first find the standard deviation and just remember that really what this denominator represents is just that standard deviation of my sample means. Either way is fine. If it's easier to just like, no, this is the equation I use, plug in these values, that's great. You're kind of thinking ahead of time, finding this first, and then just, oh yeah, any z-score I find, I always just throw the standard deviation of whatever statistic I'm looking for in that denominator of that z-score. And as we work through a few more statistics, I think thinking of it this way probably makes a little more sense, right? It'll prevent you from getting confused on some things. So that's why I like to explain it using that way. All right. Oh man, going through this quick. So we found those 2 z-scores of 1 and 2. I can think about what that visually that looks like. I can find the probability of being less than 2. Find the probability of being less than 1, subtract the smaller one from the larger one, and I'm left with what's in between. Now, how did I find these actual values? Well, I was just looking up the z-score of 1 and 2. Whoops. Looking up the z-score of 1 and 2, I just go to my standard normal z-tables, look up 1.00 as my z-score. The probability I see that or anything to the left or anything less than that, 0.8413. Look up that z-score of 2.00. The probability I saw something 2 standard deviations above the mean or anything less, 0.9772. Because I wanted the area that's in between the two, I subtracted the smaller one from the larger one. Any questions on that before I move to the next one? Let's see. Okay. Okay, we've got another example here. So let's say I've got that length of the pregnancy to the gestation weeks variable. I know the population mean is 39, and I know the population variance is 9. If I take a sample of 81 births, what's the probability that the mean gestation weeks is above 39.5? Okay. So right away, I'm drawing this out. I know that I'm looking at this distribution of my sample means. I took a sample of 81 births, so that's definitely over 30. Central limit theorem's met. I know those sample means will be normally distributed, and the mean of those sample means will be whatever the original population mean was, which I was told was 39. Now, I could have ahead of time also found the standard deviation of my sample means. This is just the square root of the variance over the sample size. I was told the variance is 9. Sample size is 81. If I actually put that in my calculator, I'll get 1/3. Okay. The question then asks, well, what's the probability I see a sample mean from those 81 births that's over 39.5? Well, right away, I know this probability has to be less than what? 0.5, because the area to the right of the mean is 0.5. I want an area that's smaller than that. So if I looked at those possible answers, I think I can rule out 2 of those. So I know it has to be less than 0.5. So I know that it can't be 0.56 and it can't be 0.93. So it's got to be either A or D. Now here's something I want to point out. If I just looked at this, I might incorrectly think, well, 39.5 is not very far away from 39. So the area to the right of 39.5, if it's really close to the mean, that area should be closer to 0.5. And I might start out thinking, well, it's probably D then. Well, if I actually work through this, not quite, right? Because even though this isn't very far away in terms of the number, remember, the standard deviation is 1/3, right? So this is actually more than a standard deviation away from the mean. So when we start to deal with these sample means and other sample statistics, we can't just look at how far away from that mean it is, because when we start taking high sample sizes, this is going to decrease our standard deviation pretty quickly. And then being like 0.5 away might be several. Like if I had taken a sample of size 200 or something, and I end up with a standard deviation that's like 0.1, well, now I'm 5 standard deviations away, and that's very unlikely, right? So don't get too lost with that these values are close to each other. We still have this standard deviation we have to think about. But what I want to do here is convert this into a z-score. Once I have this z-score, I can look it up in the table. The table will tell me the area to the left, right? But I want the area to the right, so whatever value I find, I'll subtract from 1. Okay? Oops. But how do I actually calculate this z-score? Well, I could use this equation that, whoops, sorry. I was a little bit further in my last class. I'm mixing things up. So to find that z-score, I could take the cutoff value I'm interested in, subtract the population mean, divide by population variance over my sample size. The cutoff value I'm interested in is 39.5. The mean of my distribution, 39. So the variance originally was given to us to be 9. Sample size was, what, 81? And this will spit back out at us that z-score of 1.5. I then looked it up in the table. The table tells me the area to the left. I subtract it from 1. That's fine if you want to do it this way, right? But if I'd already done this previous work, I also know that the z-score is just going to be, take that cutoff value for x, take that cutoff value for the sample mean or x bar, subtract the mean of those sample means, and divide by the standard deviation of those sample means. Well, remember, the mean of my sample means was just the original population mean, so I could plug 39 in here. The standard deviation of my sample means I calculated was 1/3, plug that in. The value I'm interested in is 39.5. If I do that, I'll actually also end up with that same z-score of 1.5. So either way, whichever way is more comfortable to you, you can do that. This is just another way of doing the same thing. Okay? Once I have that z-score 1.5, nothing has changed from what we talked about earlier this week. I look up that z-score of 1.5 in my table. So 1.50, because 1.50 is the second decimal. 0.9332 is the area to the left. So if I have this red area, which is the area to the left of 1.5, which is 0.9332, then the blue area, or this area to the right of it, which is what I wanted, I would just subtract that 0.9332 from 1 and get that 0.0668. So even though 39.5 is close to 39 here, it's 1.5 standard deviations away, which is pretty unlikely, right? Only a 6.7% chance I see something that far away or further. And notice when we start to take these high sample sizes, this is nice because when I did a high sample size of 81, what I'm really saying is the probability I see something that's more than what, 0.5 away from the actual population mean, the probability I see something that far away from the population mean or even further away is only like a 6.7% chance, which is good because now I'm thinking, okay, so my sample should be giving me a value that's closer to what that true population mean is, especially if I wasn't able to observe that population mean, right? Which is kind of what we'll eventually start talking about towards the end of next week, which is confidence intervals, probably next Wednesday and Friday. Okay. Are any questions on any of this before we get out of here? I guess I'm asking you, and then if there's anything in the chat here before. Otherwise, we'll kind of end there. We'll talk next week, not about sample means, but what if we wanted to deal with sample proportions, right? Which is going to be this variable of maternal smoking, right? It was a proportion because it was just a 0-1 variable, so it was really just telling me what proportion of mothers smoke. It'll be very similar to what we did with the sample mean distribution, but some things will be a little bit different. Right? So we'll do that on Monday. We'll get that next Learn Smart assignment up as soon as I get back to the office. So that's due Wednesday before class starts. Online quiz, that's due Monday before class starts. Other than that, enjoy the nice weather, have a good weekend, and I'll see you on Monday.